All right, hi everyone, and welcome to Active Asteroids and, in again brackets, exocomets. So we're going to start off today with a lovely review talk by Hsieh, who's going to talk about active asteroids, recent results, and future prospects. All right, so please take it away.
All right, is that good? Seems good. Great. Okay, thanks for that introduction, and I'll start my clock. And thanks everyone for sticking around for the last day. I know I get tired as the these week-long meetings go on. But yeah, I just want to also thank the organizers, of course, for putting together this great meeting, bringing us all together to discuss interesting things, and also, of course, for the opportunity to talk to you today about active asteroids. So my name is Hsieh. I'm with the Planetary Science Institute, which is headquartered here in Tucson, but personally I am in Honolulu. So, since this is solar system in context, I thought I'd try to think about why small body people do what we do. And I think a lot of it boils down to we want to try to infer details about the early solar system's temperature, compositional, and dynamical structure, and also learn about the solar system's, learn about the solar system's formation and evolution, just at a very high level. So with that set up, for those of you who don't think about small bodies a lot, you might just think of them as just one big mass of things, but there are several different subgroups, of course, and two that I think are useful to compare and contrast are asteroids and comets. So they differ in many different ways, are kind of classically considered two different kinds of small bodies. If you look at through a telescope, comets look fuzzy and asteroids look like point sources. Let's try this laser. Yeah, so so they're observationally different. If you go to them with spacecraft, which we've done for several asteroids and comets at this point, we see that they're also physically different. Asteroids are kind of these rocky or metallic inert objects, and comets are usually ejecting material into space. They're icy. Comets and asteroids are also dynamically different. Most asteroids are found in this circular orbits between the orbits of Mars and Jupiter in this area called the main asteroid belt, while comets typically have much more eccentric and inclined orbits because reflecting kind of their origin in different parts of the solar system. So asteroids are pretty much kind of assumed to have always been in the asteroid belt, or at least delivered there very, very early. While, as Kat told us yesterday, comets come from the outer solar system, from the scatter disk or cloud. So that brings me to the main topic of my talk, active asteroids. So these kind of blur the lines between those two groups. They're not the only types of objects, but they're a pretty interesting set of them. So they're basically defined as being objects, small bodies that exhibit comet-like mass loss, but have asteroidal orbits. So these are images of several examples of active asteroids. So you can see they, if you just showed somebody a picture of this, they would say, yeah, sure, it looks like a comet. They can be divided into two subgroups. One is a group that we call main belt comets. So these are objects that are in the main asteroid belt, as the name suggests, and the mass loss is specifically due to sublimation, we think. The other kind of big subgroup of active asteroids is the disrupted asteroids. And so these are objects that are basically mass loss, that have mass loss due to anything other than sublimation. So sometimes it's impacts. So, okay, I won't do it. But normally I like punch my hand. But basically like an impact crashes into another asteroid and debris flies out. And so that's the activity that we're seeing. Or sometimes we think some of them could be due to rotational destabilization. So an object is spinning so fast that material actually flies off. So dynamically, just to give you a flavor, this is a semi-major axis versus eccentricity plot. And the gray dots are asteroids and the blue dots are comets, classical comets. And all the other colored dots are active asteroids. So you can see, even if you don't really know too much about dynamics, you can just see that active asteroids seem to have much more in common with main belt asteroids than classical comets. So why do we care? So as I mentioned, active asteroids are part of this overall asteroid comet continuum that's kind of emerging, has been emerging over the last 2 decades or so. Basically, they're not separate, but there's kind of a range of objects with different properties. Main belt comets in particular, we think could be useful for studies of things like delivery of terrestrial water, solar system formation, and resource utilization. So that's basically spacecraft trying to find, water for rocket fuel, for instance, on their way into deeper space. Building on what Kat was telling us yesterday, the main asteroid belt is now the 3rd recognized source of comets in the solar system, and the only one in the inner solar system, the warm inner solar system, where it maybe was unexpected until fairly recently. And disrupted asteroids is not my main focus, but I think they're also really cool because they provide opportunities to study physical processes like impacts and rotational destabilizations in the real world and in real time. So I'll get into that a little bit. To say a few more words about main belt comets, like I said, their activity we think is due to sublimation, which makes them analogous to classical comets, which are icy. We think, as I mentioned, they're in the inner solar system, so they're in a much warmer environment than comets are normally thought to come from. And so we think the ice is probably preserved in subsurface reservoirs over a large fraction of the age of the solar system. And then the activity is just triggered recently, for instance, by an impact that excavates a crater that exposes subsurface ice. So this is just the idea that we have. Sublimation is, until very recently, has been typically inferred indirectly from 2 main characteristics. One is long duration dust emission. So this is dust that is ejected over a period of several weeks or months. And then recurrent activity near perihelion. So just like a regular comet, every time it comes close, it turns on and it goes away, turns off and then comes back again. And so these 2 properties are actually very difficult to explain as the consequence of impacts or rotation, because you don't expect an impact to hit every time it comes, close to the sun. It doesn't, and it's very natural to explain as sublimation. So there's many things I can say about main belt comets, but I will just kind of focus on this last one because it's been the kind of the most contentious one over the years, that people want to know, is this really sublimation? Like, indirect evidence is fine, but we want to see confirmation. So so this kind of set off kind of a 15-year effort to try to detect any kind of outgassing from a main belt comet using some of the biggest telescopes in the world, including a space telescope that's Herschel over there. And since we're being hosted by NORLab, I would just point out, I want to give a special thanks to NORLab and Gemini in particular. That's been very crucial for not just the search for sublimation, but just studying active asteroids in general. So it's been great. Unfortunately, as you might see or guess by the way I set it up, these were unsuccessful. So we had limits in the 10 to 24, 10 to the 25th molecules per second range. But crucially, most of these were derived by searches for proxy species because water is hard to detect from the ground. So a lot of these searches were searching for CN, which is normally accompanies water in comet spectra from the ground, and then just converted into water, assuming comet-like composition, which is not great, but it's the best, basically the best that we had, we were able to do at the time until JWST, yay. So for many, like for many of you, JWST really changed the game for us. So here's the big reveal. So this was a paper led by Mike Kelly in 2023 and included myself and Dennis Bodowitz, who's here too, among others. So this is, the white line is the Main-Belt Comet 238P read, and just for comparison is 103P, which is just a You can consider it just an ordinary comet. So, so water vapor was directly detected at 10 to the 25th molecules per second by NIRSpec. And this single detection, kind of validated our indirect method of detecting sublimation. So that was really great. Interestingly, there is a notable lack of CO2, which normally accompanies water, is detected along with water. So you can see in our comparison spectrum, there is a CO2 line, but our main belt comet doesn't have it. And this is, the upper limit is like the depletion ratio is much lower than expected. So it doesn't seem to have anything but water, which is interesting. And so a question that is still open is whether this is a question of formation circumstances, like it never accreted hypervolatile species, or if it went away during its time in the main belt. So just to let you look at this really nice result again. Fast forward to today, we have now observed 4 main belt comets, so we're slowly building up our sample. We have 2 papers on the last 2 targets in progress right now. So water vapor was confirmed in 3 of the 4, so the first 3 here. And the last one was not detected, but we think it's below the detection level of even JWST because it's clearly active in both near-cam and ground-based observations. And the hypervolatile depletion, so this includes CN, which I mentioned earlier. So all the non-detections of CN probably didn't mean anything really, because we don't even expect, we now know that we don't expect hypervolatiles in these objects. So we've confirmed the hypervolatile depletion in the first 2 objects. In the last 2, the water detection level is actually so low that the limit doesn't really give us any meaningful information. So just to kind of give you a flavor of what we're trying to do, we're trying to sample the main belt comet population in different parameters. So the symbol sizes here are proportional to the size of the object. So we're trying to sample objects of different sizes, different orbital elements, distance from the sun and inclination, things like that. And this right panel shows the location of the object when it was observed. So we're slowly trying to fill in things. Only so much you can do with 4 objects at the moment. But here's just some more teasers of, we can plot the water production rate as a function of the orbit, semi-major axis, and the location of observation. So I'll move on to impact disrupted asteroids. So these are, to remind you, these are active asteroids where the mass loss is produced by impact events, so ejecta from impacts. And here are the first 2 disrupted asteroids that we think that we've found. So you can see they look a little bit stranger than your normal comet, which maybe is a hint that something else is going on. So I'm going to focus in particular on the second one, which I really like because I think it's one of the most clear-cut examples of an impact-disrupted asteroid that we have. And also this is, I really like it because it kind of, a particular study about it combined observations, modeling, and lab work, which is often kind of ignored in a lot of people's studies. But I think all those things kind of came together to give a really good picture of what was going on. So this is a impact lab experiment where they basically fired a projectile into a surface, and you can see what happens. Sorry. Okay, so I will just move to this thing so you don't get distracted. Okay, so so this is the weird thing that we saw in a telescope, and for a while people didn't really know what was going on. It is not really like anything we'd ever seen before, but when we kind of put it together in this paper by Masateru Ishiguro et al. We think that basically this asteroid got hit by an object at like an oblique angle. It produced a hollow impact cone that had more material ejected in the downrange direction. And if you then apply radiation pressure, you turn this whole thing sideways and apply radiation pressure in that direction, you basically flip this cone inside out like an umbrella, and you can get these interesting looking plumes, which has an overdensity in one side and less on the other side. And because it's hollow, it means that the optical depth is highest in the edges. So that's how you get these plumes that look like two different ejection events, but it actually is just two sides of a single impact cone. And you see the match is actually very good, which I think is really cool. So why do we care about these? So we can learn a lot about the material of an active asteroid, of course, due to from the properties of the impact. Also, interestingly, well, if you think about it, impact should expose subsurface material, as I kind of mentioned earlier. And actually, Dennis wrote this great paper in 2014 about Hsieh, where he compared light curves before the impact and after the impact, and the blue is after. So you can see the light curve actually changed between the two periods, and the impact seems to have uncovered brighter material, which is over a significant fraction of the object, which is cool. So we can learn a lot about that. Or we can learn a lot about asteroids from impacts. So this is the other unequivocal example, I think, of an impact disrupted asteroid, because we actually caused it. We as in like humans. So this was the DART impact, which was a planetary defense technology demonstration in 2022. So we crashed the spacecraft into an object, and it created this crazy dust cloud, which was cool. If you want to know more, you can Google it. And I'm not just saying that to be lazy, but it has you may or may not find an interesting Easter egg in there. So just mentioning that. So in this case, this was in a binary system, and the satellite was the one that got hit. So you have some interesting, even more interesting dust behavior. But basically, this just, I think, is a good example that we can learn a lot about systems, maybe even just detect something that is a binary due to the properties, based on the properties of the impact. So moving on to rotationally disrupted asteroids. So these are, as I mentioned, asteroids that kick off material or even disrupt entirely due to fast rotation. Because most asteroids we think are held together by gravitational forces and maybe a little bit cohesive forces, and if they spin fast enough, they can disrupt. And similar to impacts, we can learn about the interior structure of these objects. You can do theoretical plots of what kind of densities are stable under certain spin periods and when they're not, when they're expected to break up. And we think that activity the spin up could be caused by YORP, which is a radiative effect from solar radiation. This is just another figure showing you can learn about the different, you can differentiate between different internal structures based on the outcome of a rotational disruption event. So those are kind of the main groups of active asteroids, but there's just things that we just don't know about really yet. So Bennu, famously, this is a target of the OSIRIS-REx spacecraft, which went to Bennu to try to grab some material and bring it back to Earth. But when it arrived there, it was found that it was actually ejecting material into space. And this was completely unexpected. And it just raises the question of how many other asteroids are active at this level, because this was undetectable from the ground. Maybe everything's active, who knows? So this is very much an open question. So to return to the context, I will remind you again of what I think is the point of what we're doing, to try to learn about the early solar system and the modern solar system. So for active asteroids in particular, I think there are three, or I just listed three things here, which I think we want to try to do with active asteroids. So one is to probe the present day water distribution in the inner solar system. We want to understand the processes that affect small body evolution over the age of the solar system. And we want to ultimately maybe try to use this information to infer the total water distribution in the early solar system. So there's many steps that are involved. First is figuring out what the observed main belt comet distribution is, and from that somehow infer the true main belt comet distribution. And then not every icy asteroid is active, so then we want to use the active population to determine what the inactive population looks like. And then that's in the present day, and then we want to backtrack it to the early solar system, and then somehow use that to understand the habitability in our solar system, and then understand the habitability in other planetary systems. And if there are any South Park fans, you know what the last step is of course profit. So of course there are many steps that it takes to get from one step to another, and as you can see, some of them are a little bit easier to pick up, thanks, or a little easier to pin down than others. So yeah. Okay, so I'll try to talk about quickly some of the things that we do have some idea of how to address. So we've heard about Rubin. We heard about Rubin on Tuesday from Mario. So basically Rubin LSST, I don't think I have to say too much, will hopefully detect many more objects, but we will need effective and efficient methods of following them up and also detecting them in the first place. But it should help a lot. Colin is going to talk about citizen science's role in discovering active objects. And I'll just mention that he will be talking about it later, right after this talk. So I won't dwell on this too much. In terms of moving from the observed active population to the inactive, we need to know something about how these actually are triggered. So I mentioned earlier that subsurface ice could be exposed by an impact, but recent studies have suggested that maybe rotation could also trigger material, either trigger material being lost or just shifted around on the surface, and maybe uncovering icy subsurface material that way. So this is also an open area of work, but also I would just highlight that it suggests that main belt comet activity could involve the action of multiple things, including rotational disruption and impact. So that kind of ties all the active asteroids together again. Okay. We also know about different, there's been a lot of effort over the last decade or decade and a half in terms of mobility of planetesimals in the early solar system. So there's especially driven by planetary migration. I won't talk too much about that either, since I'm running out of time. There's also possible mobility in the current modern day solar system, where we think that at least some Jupiter family comets, so these are your classical comets, could actually evolve into the main belt, at least temporarily. So we want to be really careful about this when we're analyzing things like the water production rates and depletion rates. But it does seem there might be different populations, even just within the main belt population. So I'll finish with just a rundown of some open questions. I didn't mention D/H at all. Many of you are well aware of the significance of D/H, and we would like to know what it is in main belt comets, but we don't yet. So we'd like to know that. Also other isotopes if possible. It seems like really simple. Referees ask this all the time, and the answer is we don't know how much water is in a single main belt comet or in the entire asteroid belt. So this is obviously a key thing we need to figure out how to do, and we don't, so we're working on that. And I'll just kind of pose this question, especially given this audience, just to ask, how important should delivery of icy planetesimals be considered in the habitability of planets? Because from what I've experienced, I think this is something that solar system people care a lot about, but exoplanet people not so much, and I'd love to talk to people about that. And I have had some conversations already this week, which has been really great. Yeah, so future challenges, LSST, like I said, will help a lot, but unfortunately, but also hopefully, the individual characterization efforts that we've been using so far will be unsustainable in the LSST era. So we need to figure out how to scale that. And as I mentioned with Hsieh and some other things, I think using multi and interdisciplinary studies will be necessary really to really kind of get at some of these key questions. So with that, I will just put up my key take-home message slide. And if you take nothing else, I will just say that the asteroid belt is a much more interesting place than maybe people previously recognized. So thank you.
All right, questions. Let me just, there you go.
Henry, thanks for starting the day off. Such an exciting talk. I have two questions. First, to what degree can you validate your impact models on asteroids using results from spacecraft impacts like DART? And secondly, I hope I didn't miss it looking at an email or something. Did you mention it seems that one could invert for the impactor mass and start to really probe the very tiny in size distribution in the main belt?
I'll answer your second question first, because this is something I am very excited about, and I think is very interesting. Yeah, so these impactors are probably on the 1 meter scale, which of course is too small to see even with LSST. So there's some idea of like, if we can, with LSST constrain the active population and then say, okay, these are all due to 1 meter impactors, we could get at, somehow the density of this, and maybe even the density as a function of orbital elements and stuff like that. I think that's a goal that I'm very interested in, but I think it will be very difficult because of, like I said, I think we're not entirely sure about if we see activity, what it's actually due to. Your first question about what you can learn, so for impacts, we want to, there's thermal models that tell us how deep water ice might be on these objects. And so learning how deep an impact can dig into the surface will be interesting. Yeah, but it will depend on the density of the impacted material and stuff like that, the porosity. So yeah, I think these are all questions that we're aiming for, but they're quite complicated. So it might take a while, but yeah.
Awesome.
Hi, Henry. It's a really cool talk. I'm intrigued by your speculation that maybe all the small asteroids are active after the OSIRIS-REx, but are there limits to that? Like, if all asteroids are kind of shedding material, even if individually can't see them, they should be contributing quite a bit of material to the near Earth space. So are there limits to how much you could actually be shedding from these things? From the fact we don't see dust streams on every single small asteroid.
That's a great question. I think the answer is I'm not sure yet. I don't think anyone is sure yet. I mean, there's a zodiacal dust, of course, so that's, there could just be, there's dust. There's a lot of dust contributors to the zodiacal dust, which is just dust in this plane of the solar system for people not familiar. I do have some thoughts about taking many asteroids and trying to combine them all together and try to find dust. There's probably asteroids that are more likely to have dust than others, like recent family members from a recent collisional disruption, or fast rotators. So if you kind of group them in certain groups strategically, maybe you could find evidence of this. But this is definitely kind of a newish development, of course, because OSIRIS-REx was fairly recent. So.
Right, one quick final question.
Yes, so there's some discussion in using the OD stretch line at 4.1 microns combined with robust measurements of other ice features in the spectrum of planetary bodies. Do you think that this technique could be applied to spectra from JWST of your main belt comets to determine their D to H ratios?
From everything I understand, I don't think the water production rate is high enough to get D to H, get isotopes, but it's not my area.
This
So,
is on ice, not water vapor.
oh, okay. Well, so ice is also, it's even harder because these are mostly small objects. And so even just getting reflectance spectra is difficult for them, especially when they're contaminated with dust when they're at their brightest.
Great. All right. Well, let's thank our speaker again.